So we're talking about the Hirsch conjecture, and we said that the Hirsch conjecture basically tells you that it basically tells you that you can walk around a polytope quickly. So if you want to go from any vertex to any other vertex of the polytope, then you can do it in only n minus d steps, staying on the edges, right? So a step is a step along one of the edges. So Hirsch conjectured that the largest that you needed was n minus d steps. Okay? But as I told you last time, this conjecture is not true, and this is the most exciting recent development in the theory of polytopes. About 3 months ago, Santos announced the proof that this is not true. Okay? And so what I want to do is basically give you a brief sketch of some of the main ideas behind this proof. And as I told you already, a few of the details of what I'm going to tell you about, you're going to fill in the homework. So basically, I'm gonna tell you what the general idea is, and you can basically prove what I'm going to say. But of course, there's a lot more that he did, and we can't do it so quickly. And I think it's a good topic for the project if you really want to go in depth and understand the whole proof. But this is how he did it. So the first step is the following. There's something called the d-step conjecture. And the d-step conjecture seems like it should be easier because it's just a special case when n is equal to 2d. Okay. And so, of course, the Hirsch conjecture would imply the d-step conjecture. That's obvious. But the nice thing, actually, is that this is an if and only if. And this was an observation of Klee and Walkup that actually these things are equivalent. So this is obvious. But they showed this. Klee and Walkup. And so that's the first thing that I want to outline is how if you can prove that the Hirsch conjecture for n equals 2d, then you have proved it for any value of n. So somehow the hardest value seems to be n equals 2d. Okay. So here's a proof that d-step implies Hirsch. Well, a sketch. So the point of this conjecture is somehow that the hardest value to prove it for is n equals 2d. And so we're going to do two cases, n less than 2d and n bigger than 2d, and reduce those cases to this one. Okay. So suppose that you want to prove the Hirsch conjecture for n less than 2d. Okay. Then what they observed is the following. If n is less than 2d, that means that you have very few facets. Okay, you're in dimension d, and you have fewer than 2d facets. And what they show is that basically the facets are crowded in the sense that for any two vertices, you can find a facet that they're both on. For any u and v vertices, there is a common facet that contains them both. There is a facet f containing them. Okay, and this is something that you're going to prove in the homework. And so you have your polytope here. I don't know. So imagine this is a three-dimensional polytope, maybe. Okay. You're trying to get from u to v. And basically the idea is that you take these u and v. You want to show that you can get quickly from u to v. Okay. What you do is you say, okay, u and v are in a common facet, so consider that common facet. Okay. So maybe it's this one over here. And then you're basically going to say that by an argument of induction, you're going to do an induction argument on the dimension, and you're going to say, well, if I look at the Hirsch conjecture for the polytope F, that's a smaller dimension, and so I can assume that inductively that I already proved it. Okay? The point is basically that to get from U to V in the big polytope P, well, because U and V are in the same facet, then you can just kind of inductively do it for the smaller polytope F. And you're basically going to say that, sorry. So this is basically telling you what's the largest number of steps it could take you to go from U to V in the polytope. But then I'm just going to say, look, just forget about the rest of the polytope and look at the facet only. Okay? And I can just walk on the facet. Okay? And get from U to V in at most this number of steps. Because from U to V I can get in d-1 steps because I'm in a d-1 dimensional polytope. Right? And this polytope has at most n-1 facets because it has fewer facets than the big polytope. So what they show is this. Okay? And again, you're going to fill in the details of why exactly this is true. But these are the two steps. First, they observe this, and then they use it to prove this. And then once you've done that, then, for example, if you want to prove it for, I don't know, n less than 2d. So let's say d is 8 and n is 12. Okay? Then you're just going to say, okay, well, n is less than 2d, so applying this, I'm going to get that this is less than or equal to delta of 7, 11. Okay? N is still less than 2d, so this is less than delta of 6, 10. Here, n is still less than 2d, so I apply it again. And I get to 5, 9. Okay? And then you've reduced it to a case where n is not less than 2d anymore. So if you can prove it for this polytope, then you can prove it for this one, because if you can prove it for this polytope, then you would get that this is less than or equal to 4, which is what you wanted to prove. So you've reduced it from the case n less than 2d to not that case. Okay? So that's the first step. The second step is if n is bigger than 2d. And then the lemma that you prove is similar. You prove a lemma that says that for any u and v in any vertices u and v, there is a facet that doesn't contain either of them. Okay. So you're going to say, let's say that you want to get from u to v quickly, okay? And then in this case, the lemma that you prove is that you prove this. Okay? Saying that if you want to get from u to v quickly in a d-dimensional polytope with n facets, you can reduce it to the case of d plus 1 dimensional polytopes with n plus 1 facets. Okay? So you somehow reduce it to going up a dimension, which is kind of the opposite of what you do there. And in this case, what you do is the following trick. You say, okay, I have a facet that doesn't contain either. So maybe this is the facet. And then what I want to do is build a polytope in one dimension higher. And what you're going to do is just take your polytope and kind of unfold it at F. Okay? So maybe a little bit hard to draw, but here's F, okay? And here's P. And you're going to unfold it and make like another copy here, like this. It's going to be hard to make this look three-dimensional, but maybe like this. Okay, you kind of make it open its mouth like that, and then you make a polytope like that. You make a polytope of one dimension higher, and then you prove actually that if you are able to show that, I mean, then here you still have U and V, because this were U and V. And then basically you're going to argue that because you know how to walk quickly from U to V in this polytope, then you can also walk quickly from U to V in this polytope and prove this inequality. More or less the idea. Okay. And that's what you're filling in the details for. I mean, basically, I'm just saying, suppose that you know what is the largest number of steps that it takes you to do this in d+1 dimensions and n+1 facets, and then you show that for d dimensions and n facets, you can do it at least that fast. Whatever this bound is, this one cannot be as bad as this one. Okay. And then if you do this carefully, basically this tells you that if n is less than 2d, then you can kind of push n to be closer to 2d. Here it tells you that if n is bigger than 2d, then you can push n to be closer than 2d. And it turns out that just combining these two arguments, you can just reduce it to that exact case where n is equal to 2d. So n equals to 2d really seems to be the hardest number of facets for this Hirsch conjecture. This is a sketch. Okay, you'll fill in the details, and as you know, I'll be happy to help you with that. But that's basically the sketch of how the d-step conjecture implies the Hirsch conjecture. Okay, and so that's the first part. Is reducing to the d-step conjecture, and so then what Santos did was disprove the d-step conjecture. Okay, and the thing is that if you think about this d-step conjecture, actually, if you think about the polytopes of d dimensions that have exactly 2d facets, they're very special. Okay, especially considering that by the first part of that argument, if two of your vertices are on the same facet, then an induction argument is gonna do it for you. Okay, so then really the trouble polytopes, the hardest polytopes to prove this for, to prove the Hirsch conjecture for, basically tell you should be in a situation where you have dimension d, 2d facets, and you're trying to get from a point U to a point V, and these guys don't share a facet. Because if they share the facet, then you can do the induction argument that you did over there. But you see, how many facets have to contain U? If you're in d dimensions, you need at least d planes to cut a vertex. Right? Think about it. To determine a vertex, you need to intersect at least d equations. That's linear algebra. Okay? So that means that you have to have at least d facets here. And by the same reason, you have to have at least d facets here. And then if you think about it, there can't be anything else. There can't be any more facets, right? Because you only have 2d facets. And there's no common facets between U and V. So somehow the polytopes that are troublesome are precisely the things that look like this, where actually you have to have equality here. You have to have equality here. And so what you have are polytopes that look kind of like this. And I'm going to try to draw something. Something like this. Okay. These are kind of the hardest polytopes for the d-step conjecture. Okay. And Santos calls these spindles. Is spindle a word? I guess it is. It's something that spins like this, I guess. Yes? What is a spindle? Ah, okay. Oh, okay. Yeah, spindle. Okay, so that's a good name. So then he basically said, okay, well, to prove the Hirsch conjecture, I need to prove it for spindles. Okay, and then he realized actually that to disprove it, then what he needed to find was a bad spindle, and that's what he was after. Okay. So. And then what he did is that then he proved a version of this correspondence that is specifically for spindles. Okay? So here's what he proved. He proved that if you have a spindle of dimension d and n bigger than 2d facets and diameter bigger than d, let's say diameter delta, which is bigger than d, then he used that to construct a spindle in one dimension higher. And I shouldn't say that it exists, because he tells you how to construct it. So you can construct from it a spindle of dimension d plus 1 with n plus 1 facets and diameter delta plus 1. Okay? So if you have a spindle where the diameter is delta, then you can go up one dimension and get the diameter to go up by 1. And remember, what we're trying to do is find a spindle that has too high a diameter, right? Because the conjecture says that the diameter should be d. We want a spindle with a higher diameter. So then he proved this. Okay, this was another step. And then finally what he proved, and he actually constructed a spindle of dimension 5 dimension 5, 48 facets, and diameter at least 6. Okay. So I'll tell you in a second how he did this, but the point is now you will see that if he can do this, then he can disprove the conjecture. Why? Because he can start. Well, so first of all, let's talk about this. Does this violate the Hirsch conjecture? No, because the Hirsch conjecture tells you that it should take you at most 43 steps. And we're talking about diameter 6. That doesn't really say anything. This is not even close to violating the Hirsch conjecture, right? But through this trick, he's able to bump up the dimension until he makes it break. Because using this, then this tells you can bump up the dimension by 1, the number of facets by 1, and the diameter by 1. Okay? And then n is still bigger than 2d, so he can do it again. Bump dimension by 1, number of facets by 1, diameter by 1. Dimension is still bigger than 2d. So you can keep doing this until the dimension is equal to 2d. Okay? So when is that going to happen? Well, you see that the difference is 43, right? Between the number of facets and the dimension. So when you get to dimension 43, you will have reached 86 facets. And then what is the diameter going to be? At least one more than this. At least 44. And that is the counterexample. Because according to the d-step conjecture, a polytope of 86 facets in 43 dimensions should have at most diameter 43. And so that was another very nice insight, was that to construct these higher dimensional examples, he could just kind of lower the dimension and try to do something in a dimension that's more manageable. So this is kind of the punchline that, okay, so theorem Santos, there exists a polytope of dimension 43, 86 facets, and diameter greater than or equal to 44, and therefore Hirsch is not true. Okay. But really, he got his hands dirty here, not here. Okay? And this inductive argument is not too difficult. And the main insight was actually that you can bring this back to a small dimension and then construct something like this. So then this is basically what we need to do. Okay, and then the question then is, how can you construct a 5-dimensional spindle? That still is not so easy.
Isn't that really the main thing? That lemma right there?
Yeah,
I mean,
yeah.
That there is, I mean, as long as you can build infinitely many of these. Yeah.
I would say it's a combination. I mean, so I would say that this insight is very good, and this insight is very good. So, and these are. This was done before him. So his two main insights, I guess, were these two. Okay. I mean, this and this construction. Okay? And he's amazing at constructing examples like this. But the point is actually that the way that he did this is by coming up with. I mean, there is something called I'm blanking on the name now. The Schlegel diagrams. So there is something called the Schlegel diagram, which allows you to view a 4-dimensional polytope. So somehow 4-dimensional polytopes we can kind of deal with. Okay? And 5-dimensional polytopes are maybe a little bit harder, but the fact that it's a spindle makes it easier, because that means that actually all the action of this polytope is here. So it's really only kind of 4-dimensional action. That's basically the idea. By being 5-dimensional, but being a spindle, that means that you're really only kind of 4-dimensional. And there is a trick to go from a 4-dimensional picture to a 3-dimensional picture. And so really, his argument is kind of a 3-dimensional argument. And it produces a 5-dimensional polytope, and then he builds it all the way up to the desired thing. So that's basically the idea. It's a very rough idea, of course, but it's a very cool argument. And if you guys want to look at the details, I think it's a reasonable project to look at and understand this proof. All right. But again, let me make the point, the very important point, that this is just scratching the surface, and we have no idea whether this function delta of d of n is big or small. There's very little that we know, and this is probably now it's going to become an even more active area of research now that people all of a sudden are going to psychologically find it within reach. Because if you work on a problem that hasn't had progress for 53 years, that's kind of scary. But if you have some very fresh ideas, then you think, okay, maybe I can jump in here and get something out of this. Okay. So that's all I wanted to tell you about the Hirsch conjecture. You'll do a little bit more in the homework, just to give you an idea of some interesting news in the theory of polytopes. I'm sorry? Yeah, yeah. Hold on, let's get this on microphone. This is important. Actually, why don't you get there so they can see you too?
So I just wanted to add, I'm Tristram Bogart, by the way. I was at the conference in Seattle a couple of weeks ago where Francisco Santos presented this proof. So one thing he stressed is that although this is a 53-year-old problem, Vic Klee, who's a mathematician in Seattle for years and years, recently deceased, who the conference was in honor of, Klee had kept saying he didn't think the Hirsch conjecture was true. So it's a little more encouraging to work on something like this if you have somebody, somebody famous and has thought a lot about it, saying there ought to be a counterexample. I think that happened.
He is one of the two that proved that reduction to the d-polytope conjecture. He was an expert on
Yes.
But I think also this points to the fact that, I don't know, maybe people thought this was harder than it really was. Of course, it's easier to say it after the fact. And I really think that if somebody was going to come up with a nice example, it was very likely to be Francisco Santos. He's very, very, very good at this. But I mean it that the proof is something that you guys can read it over the next couple of months and understand it. So. That's also a nice thing about a field where you can see that you can get very exciting things with reasonably simple tools. Okay. Okay, so the other thing that I want to tell you today is a little bit more about the graph of a polytope. I want to talk about something called Balinski's theorem. So let me just introduce a little bit of terminology from graph theory. So we say that a graph is connected if there is a path between any two vertices. Okay, so for example, this graph is connected, and this graph is not connected. Okay? And we're going to say that a graph is deconnected if it's more than connected. It's very connected in the sense that you could delete any d-1 vertices and you're still not going to be able to disconnect it. If it is still connected after removing any d-1 vertices, or fewer vertices and all incident edges. Okay. So, for example, how connected is this graph that I drew here? Connected is saying the same thing as zero connected. Okay. Or no, connected is the same thing as one connected, because one connected means that you remove zero vertices and you're still connected. Now, is this two connected? Yes or no? Why is this not two connected? So two connected means that if you remove one vertex, it's still connected. So if you remove this vertex and the incident edges, it's connected. If you remove this one and its incident edges, it's connected. If you remove this one, it's connected. So that graph is also two connected. Is it three connected? Can you disconnect it by removing two vertices? You can remove the top and the bottom vertex, and you will have disconnected the graph, right? Because that means that you lose all these edges. So that means that this is not 3 connected, but it is 2 connected. Okay? So somehow a measure of how connected you are. Okay? And so Balinski's theorem is very nice and very simple. And it says that d-polytopes are deconnected. So if P is a d-polytope, then its graph is deconnected. Okay. So that tells you, for example, that if you have a graph that is only 7 connected, but not 8 connected, then that cannot be the graph of an 8-dimensional polytope. Okay? And so that's kind of a nice thing because it tells you a little bit about the structure of to what extent can you look at the graph and read off something about the polytope. Okay? And that's something, this is a combinatorial notion. So we're saying if you take a graph and it's not 8 connected, then it cannot be coming from an 8-dimensional polytope. So that means that you can say something about the dimension from the graph. Okay? Now, let me first start by pointing out a very simple corollary, but an important one, which is this. The degree of a vertex has to be at most d. So why is that a consequence of Balinski's theorem? Well, imagine that you had a vertex, and that vertex had all its neighbors were like this, d minus 1 neighbors in the polytope, okay, and then here's the rest of the polytope. If this was the case, then by deleting all the neighbors of V, you will have deleted at most d minus 1 things, and you will have disconnected the graph because V is disconnected from everybody else. Okay. So in particular, that's one way to think about deconnected things. Deconnected things, in deconnected graphs, every vertex must have at least the edges coming out. Okay. It's a pretty connected thing. Okay. By the way, we knew this already. We knew that the degree of a vertex was at least d, but this is a nice combinatorial proof. Let me say that one reason that we know this, let me give you another quick proof of this in words. We talked about how these rays that come out of V span a cone that covers the whole polytope. So if the polytope is d-dimensional, then to cover it, you need at least d directions. You need at least d independent directions. So that's another proof that the degree has to be at least d. Okay, so let's prove this. So let's say that V is the set of vertices of the polytope, and let's consider a set of at most. Let's consider a set of d minus 1 vertices and delete them. Okay. It's not too hard to adapt this proof for a smaller number of deleted things. So of course what we need to prove is that if I take the graph and I delete the vertices in S, then what I get is connected. Okay, that's what I need to prove. And I'm going to prove this by induction on the dimension. Okay. Again, this is something that might be a little bit unusual, but we are allowed to induct on whatever we want as long as the argument is logical. And so one thing that you often do in polytopes is induct on dimension. Okay, so what I'm going to do is the following. Let's say that L is the span of S. Okay? So, I mean, think about it. Here's our polytope. Maybe that's it. I'm taking, so for example, here I'm in dimension 3, and then I'm taking 2 vertices. Okay, I'm calling them S. And then I'm considering the span, and I'm calling that span L. Okay, so this is L. And I'm going to consider 2 cases. One is that L doesn't intersect the interior of the polytope, and 2, that it does. Okay. So basically I'm saying either this affine subspace pierces through the polytope, or it just kind of brushes the boundary. Okay? So the first case is that it only brushes the boundary. So if you see, that's not the case that I have here, right? Because in this case, I am going through the inside. Okay? In case 1, what I have is that the polytope looks like this. Okay? And maybe S is here. And here's L, and you see that L doesn't really go inside the polytope, it stays on the boundary. Okay? So in that case, if you look at the intersection of L with the polytope, you're going to see that it is contained in some face of the polytope, right? Because it's in the boundary. So L intersect the polytope is contained in a face F. Okay. So in this case, this is the face F. Okay, that's the face that this space touches. And we're going to say that F is given by the linear function. Well, I don't even need to write this. Let's just say that F is maximized by the direction C. Okay, we know that's what it means to be a face. It's the part of the polytope maximized in some direction. Okay? And then what I'm going to do is now look at the opposite direction, minus C, and look at the optimal face in that direction. Okay, so when I do that here, it looks like F so here F is the optimal face in this direction, and in the opposite direction it looks like this is the optimal face, right? So this is a piece of minus C, and let me call this maybe F prime. Okay, so let F prime be piece of minus C, where the, in other words, where the linear function C is minimized. Okay. Now, what's the point? What I want to argue is the following. What I want to argue is pretty simple. I want to say, look at any vertex of the polytope that is not in S. Okay? Let's say this one. Okay? And remember what happens when we did linear programming in this direction. We had this algorithm that told us how to start from any vertex and walk to the optimal vertex in the direction minus C. Okay? So starting at any vertex V. That's a vertex of the polytope, but it's not one of the deleted vertices, like this one. I can use linear programming to go all the way down to the bottom face. Okay. So starting from here, use linear programming to find a path and maybe leave a space here. Find a path from V to the face piece of minus C. Okay? And linear programming tells us that we can do this while always decreasing the C value, right? Because that's exactly what linear programming does. If you want to find the face with the minimal C value, then you start at a vertex, then either that vertex is minimal or you go to a lower vertex in that direction. Then either that vertex is minimal or you go to a lower vertex. You keep decreasing the value of C. So what I want to say here is that it's a C decreasing path from V to P minus C. Okay? And the reason that I care about this being C decreasing is that I know that all the vertices of S take the maximum C value. Okay? And so if you're decreasing the C value, that means that you cannot hit these vertices because these vertices are at the top. Okay? So that means that this path avoids S. Right? Because linear programming could never send you to those vertices S. Okay? So that's telling me that from every vertex, I have a path to the bottom. Okay? So every vertex is connected to the bottom. And then I'm going to say, well, the bottom is a lower dimensional polytope. And so it's connected by induction. So if the bottom graph is connected, okay, I mean, here it's a little bit misleading because it's only a point, right? But in general, this is a face, and it has its own graph, okay? So it has a graph that is connected by induction, and from any vertex, I can walk to that part of the graph without touching S, okay? So that means that when I delete S, I haven't disconnected the graph. So by induction, piece of minus C has a connected graph. And therefore, when I take my graph of the polytope and I delete S, this is still connected. Okay. I guess I was a little bit lax about my base case, right? So if we're doing induction on D, I should do the base case. Let's say that the base case is D equals 1, okay? So if I have a one-dimensional polytope, then I want the graph to be one connected. But the graph of a one-dimensional polytope has to be just a segment. And one connected means connected, so a segment is connected. So the base case is free, you don't have to think. And then this is the inductive step in case 1. Okay? Case 1 where L doesn't intersect the interior of P. Now let me do a similar argument for case 2. So in case 2, L intersects the interior of P, and so this is a good example of that. Okay. So what I'm going to do now is the following. I'm going to say, choose some other vertex out of any other vertex that is not in S. Okay? So I don't know. And I mean it. So Ashley, choose a vertex for me. The top one, okay. So let's call this vertex V. Okay? So just consider any vertex that is not in S. Okay. And now, how many points do I have in S union V? 3, or in general D. S had D minus 1 points, and now I added 1, so I have D points. Okay? And for any D points, I can find a hyperplane that goes through them, because hyperplanes are d-dimensional. Okay? So choose a hyperplane. So let H be a hyperplane containing all the points in S and also this new point. Okay? Sorry, hyperplanes are d minus 1 dimensional, and you need d points to determine a hyperplane. Okay? So if these d points are in general position, then they're going to determine a unique hyperplane. And if they're not in general position, then they're going to determine some smaller subspace, and I just consider any hyperplane like this. Okay? So maybe this is going to be my hyperplane in this case. Okay? H. And let's say that H has equation C dot x equals C0. Okay? In other words, what I'm saying is that the normal vector to H is called C. And then I'm going to say the following thing. I'm going to say just split the polytope open at that hyperplane. Okay? So here's the top part of it. It's kind of hard to see, but I guess really, you see in this case actually the hyperplane goes all the way down this way like this. Okay, so this is the top, and then this is the bottom. So I'm going to define P plus to be P intersect Cx bigger than or equal to Z0, and P minus to be P intersect Cx less than or equal to Z0. So I kind of cut at the equator. Okay? And then I'm going to make the same argument that if you now consider, I wish that I hadn't erased the previous picture. But if you consider the maximal direction in this face, P sub C, and the minimal direction in this face, P sub minus C, then by the same argument that I just made, you can walk from V all the way down to P sub C. And I mean, the argument that I just made basically says that all of this polytope is connected to P sub C. And by induction, P sub C is connected. And if I do the same thing here, I'll see that all the polytope is connected to P sub minus C, and P sub minus C is connected. So by induction, this part of the graph is connected, this part of the graph is connected, and they share the vertex V. And V is not in S, so that's not one of the guys that you deleted. So if both sides are connected and they have a common vertex V, that means that the whole thing is connected. Okay. So by induction, by the same argument, the graph of P plus is connected, the graph of P minus is connected, and also they share V. So, and I should say with S deleted, right? With S deleted. And so this graph with S deleted is connected. And that's the end of the proof. Okay? You guys have any questions about this proof? Yeah? Exactly. Exactly. So you see what I'm doing here is kind of reducing to the other case, because in the other case I had this situation where this orange hyperplane was an extreme hyperplane. Okay? And I wanted to reduce to that case, so what I said is, okay, well, if it's not hyperplane, if it's not an extreme hyperplane, let me just force it to be by just cutting the polytope open, and now it's extreme in both cases. Then you repeat the argument that you just did, and then thanks to the vertex that you chose for us, V, that is the key vertex that allows you to say, well, if this part is connected, and they actually have a common vertex, then that allows me to go from one part to the other part. And that shows how the whole graph is connected. It's kind of a slick proof, and it's maybe easier. It's maybe deceiving that it's very easy, but it's actually a bit tricky to get the proof to work just right. Let me tell you a nice open problem. This says that from the graph you can read something about the dimension. Like I told you, if your graph is not 10 connected, then you cannot be a 10-dimensional polytope. But a next natural question then is, if you have a picture of a graph, can you tell what dimension the polytope is? And now we know that the answer to that question is no, because cyclic polytopes, no matter what dimension they're in, they have the complete graph as their graph. Okay? So not from every graph can you determine the dimension. Okay? But here's an open problem that no one knows the answer to. If I give you the graph of the d-dimensional cube, can you find a polytope in a different dimension with that graph? No one knows. Even for the 5-dimensional cube, this is not known. Okay? And so that's a nice, simple, concrete, open question. Is there a 4-dimensional polytope whose graph is the graph of the 5-dimensional cube? No one knows. So if you want to try it out, that's another. Who knows? It might.